Recording in progress.
What is it? Recording. Okay, hi everyone. Today we are discussing this paper that is bombastically called the Platonic representation hypothesis. And the name kind of misled me at first, but then now, after struggling with it for a couple of days, I appreciate how unassuming is the name, so we can. It doesn't say that the Platonic representation hypothesis is right or wrong or anything. It's just a paper about Platonic representation hypothesis. Right? But then we will not probably go into who's Plato and all that stuff. But we may. But what is representation? That's what attracted me when I started reading this paper. And so I prepared an introduction about what is representation, what can this word mean, and then we'll talk about it. And I thought I will have time to prepare slides for LitReview, but I didn't. But you all should read their LitReview. That's why I invited you. So, but you all should read their LitReview because it's very good. I think a job covering the field and people who are actually working with this Platonic representation hypothesis on like this is in general. But what is representation is a problem. So representations, when neural networks, so complete history of ML was like, here's how much. So everyone was like, hey, we're starting working with large data, first of dimensionality, it's scary, we've got to do something about it. Well, easy. Select subset of features, and those features now represent your samples. So your data set is a huge table describing production of, production plant, lots of stuff, and there are many plants, but you only select, okay, the speed, the blah, 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 3 features, and that's what you use to classify. Or your input is an image of this room, but you only select average lightness, I don't know, the ratio between RGB, the simplex, and you got two numbers that represent entire image or entire sample. So we went from large vector in our d-dimensional space where d is very high, or image is million dimensions, to a small, tiny vector that statistical methods and machine learning methods can deal with. We ignore max margin classifiers at this time. We move on, start applying all of our machine learning algorithms, and everything works beautifully. Then finally, we notice max margin classifiers when support vector machine gets published, and then all of those representations, we toss them away, those small representations. We focus on working with kernels. Like instead of producing representations, we can pack stuff with kernels, and we can pack any stuff like we do with algebras. So we can have algebra or graphs. We can have kernels on graphs. Like we can have algebra on strings. We can have kernels on strings. So on stuff, 10 years later, we figure out, hey, but the kernels can be learned. And that's where this paper, I believe, starts. Yes. So the kernels can be learned, meaning, and I'm buying into the misleading language as this paper. I feel this paper is maybe misleading the way it presents things because the terms. When I say kernels can be learned, and the slide is true. The words are lying. A kernel is a way to avoid the mapping. So a kernel is equivalent to taking a mapping into a high-dimensional feature space or some dimensional feature space, maybe infinite dimensional feature space, and then taking an inner product in that space. A kernel is a way to just take X and Y and compute that inner product without the map. In 2012, well, and again, this slide is a joke. It kind of talks about this not fairly smart entity that is called society. Even though individual people knew all of that way before and stuff like that, but our community is very slow to recognize things. It likes new shiny, and it's not very specifically right entity. So that's what I mean. It's in 2012, everybody saw neural networks. Jeff Hinton, Yoshua Bengio, Nikun, Jan Nikun, they knew all that way before 2012. They kept talking about it. Jan Nikun specifically kept advocating for, hey, we will not need any more feature handcrafting, because if you have handcrafted features, your logistic regression will be perfect. It will be one of the best methods, if not the best, and it's fast, etc. But often the coming up with good features is very hard. So the thing is, in 2012, ImageNet moment, Alexander, etc. What we showed that we can have a neural network that we train, and then we compute assigned distance, right, or your inner products on top using logistic regression. So that's the history of machine learning. Kernels, okay, if we learn those kernels, then the system learns, the neural network, the spy, learns a space or a mapping to a space where entities or our data samples are represented in such a way that it becomes easy for the task to be solved. Whatever the task is, whatever we were training the neural network to do, the hypothesis or let's call it hypothesis, is that the neural network finds a way to arrange our data, or finds a map, not the linear map, into a space where data is arranged such that the problem is now easily solved even with a linear classifier. And we saw a talk by Mike about the San Francisco bridge and stuff like that. So, hey, everything on the top becomes linearly separable. And I'm not so surprised because, well, that was the point why we need that. That's the point of using this to make everything at the top embedding linearly separable. And so here we are, right? We're training those spies, heavily, the entire field is trained, and they're performing amazingly. Language models, image models, everything. But what are they learning, right? And are they finding that space where the data is arranged in an interesting fashion? Well, first thing I want to show you is that the data is already arranged in an interesting fashion. And this is fashion means data set. And we're looking at UMAP and TSNE three-dimensional embedding. This is not neural network. This is not doing any fancy search, training, adjustments, mappings. It tries to represent the data as it is in a high-dimensional space. It tries to represent it in a low-dimensional, three-dimensional space. And what we see, so for example, and tell me the dresses, right? Like similar kind of dresses, similar kind of t-shirts, similar kind of, I don't even know, and the shoes. Yeah, I mean, you're okay, you just said it. Like the shoes are together. They are not together because some magical entity represented like that. The data is already like that. The data, this is the typical mapping UMAP. The data is already for pants. The pants in this, I don't know, is it 42, 48 by 48 dimensional space? They already clustered together. They're near each other. And other kinds of data points like bags, they're near each other in the space. They're neighbors. We can go through them. There is no deep learning happening on this slide. We're just talking about the data. So let's talk a little more about the data. Yes. So we can. Oh, no. The heat box is a little shaky. Let's talk and use images. Let's take an image. All this stuff is arranges high-dimensional data in three-dimensional space. In order to put this high-dimensional data, 10,000 MNIST samples into three-dimensional space, it's not that smooth on my screen. We use PCA. PCA doesn't really work that well for this task. If we use Disney, so the colors are added for the digits. There are 10 colors, 10 digits, and this is just convergence of Disney algorithm. Again, the representation hypothesis, the Platonic representation hypothesis paper is about neural networks. What I'm showing you is that just the data. Before any neural network is applied, the data is highly structured. Sixes live together in the space of MNIST data. Zeros also together, and ones, fours and nines live nearby because they're very similar. They are separated, and nines and sevens live nearby because of the same space. So this is our data space. Now let's take a data space of square images. I think 48 by 48 square images. So this data space can represent anything, like a lot of stuff within this. What I'm showing on this slide, I'm taking two random images, and I am plotting many images on the line between those images within that space. And I don't see anything interesting appear in between. I don't see a plan of, I don't know, Eiffel Tower appear there or like nothing. There's still faces. Although anything could be drawn on this image, but I'm exploring this space and nothing interesting. But maybe because something special about faces and the space is misleading, it makes it look like I'm doing morphing or some stuff. But all I'm doing is it's called linear interpolation. But don't focus on the interpolation. Focus on the fact that I'm showing you all points in that space that are on the line connecting two faces that are interpolated between. So let's take all the faces and make them binary. Binary will means that, okay, how many binary images for 48 times 48? It's 2 into 48 square power, all of the possible images that we could generate. And I'm taking two images and I'm interpolating again between them, but they're binary now. So possibilities 2 into power 48 squared. And I'm interpolating continuously, not binary, but I'm hoping to find something there. And I'm not finding anything there. It's only faces. So those faces live in 48 square dimensional space. like those vectors somewhere. And anywhere I walk between them, I only see something that resembles those spaces, right? Then what I do is, well, okay, it's interpolation. I'm within the convex hull. Why don't I do this? I will take two faces on opposite sides of the convex hull and swing around. Instead of going straight on the line connecting two faces, I will go in ellipsoid, thanks to Claude and all others who are doing this for me. I forgot which one. Gemini Flash, actually, much better than but at times. And yes, now we can go out and we see, oh, some noise appears. Something's out there that is not a face, but nearby this convex hull, right? But still, the tightness, the semantic tightness of those images is amazing. Like I'm really trying really hard to see something not like a face, maybe a car, no, and the same thing continues. So the point I'm making here is the data is highly structured. It lives in some manifold in the high-dimensional space already before we training our neural network or before we do anything. Right with me? So the data has its structure by itself, and the structure of the data. That's the key. The structure of the data that I was showing to you in the last 5-10 minutes is relation. It is not about a single, it's not representation of single data point. I'm not representing anything. I'm representing, like in those images, I'm not representing anything. It's the raw stuff. That's the data. And I'm showing you the data. I'm representing images here because I took, I think it's 27 square dimensional space. Wait, 20 by 28 square dimensions. And I'm taking this space and representing it in 2 dimensions. But one remains one. The point that represents, oh, that's a nice 2 here and here 1. The point that represents this 2, well, I took the, not I, thanks for the people who have worked this from online. What we did together. Now, co-authoring, I claim co-authorship is took the MNIST images and put them on the corresponding locations. But what we're displaying here is location. So I'm not representing a single data point. Single data point is a vector of x and y coordinate. I'm representing entire data set, but I'm representing relational structure, right? If I take this thing and rotate it, relational structure will not change. The neighbors of a point are the same. If I take and flip it, the relational structure will not change. I could stretch it a little without changing the relational structure that much. But that's crucial for this paper because that's what it was like. That's what it hit me because I didn't expect. But what are all of those features, embeddings, representations, or basic? What are we talking about? Relations, are they representation or a single thing representation? Long ago, in some galaxy far away, in 2009, there was this paper published from where they looked at 3-layer neural network, CNN, and it trained it first column on faces, on cars, elephants, chairs, and all mixed together. And they show that receptive fields that are learned by the neurons different at different layers, and there is a higher level abstractions. The higher the neuron, higher level abstractions it learns. So what are those? They call them bases. Are they features? Are they representations of the data? Well, they're kind of property of the model. But when I'm thinking about representation learning, I'm thinking about learning a vector that represents another vector, an input vector. So I'm thinking back about representing a person with the date of birth and zip code and last name, and then we can highly likely uniquely identify that person, right, with those three features instead of the relational or instead of this. But apparently, that's not how this paper thinks about it. So long ago as well, in 2013, some obscure people who nobody knows published this paper because it was rejected from IPER in 2013. And the question that these people were asking was, well, simple. Can we, like, okay, deep learning neural networks are on the rise. They're powerful, and we knew that powerful back in 2001 as well. But are they useful? Will we be able to use those neural networks for discovery? Training a classifier is not what science is doing. Science is for causal knowledge, for knowledge extraction, for foraging and finding the new knowledge. So can we use those classifiers to gain new knowledge? And one thing they observed is that if you take raw data, which was MRI, gray matter concentration maps on the left right here, and you try to create a good embedding into two-dimensional space of different subjects. So there are four colors there: red and skin color, teal. No, I don't know what teal. What is that color? Uh, so the brownish color of the background of the slide is class not healthy controls 0 and schizophrenia 1. And the blue and gray colors are hold out. They were not seen by the model. Well, nothing was seen by the model in raw data. It's just the data. So we tried to. The model was trained to classify schizophrenia and healthy controls, and we see that if we train layer 1 network, it's not as discriminative. At least it doesn't push the representations. Now, representations, in my sense, the vectors that represent each individual link. Each dot here represents a representation. So we have a volume of concentration maps. This volume goes through a neural network, creates a vector. This vector then gets mapped by a simultaneous neighbor algorithm, which will come up with this paper again, into the two-dimensional space. This is not TSNE, UMAP, or anything. This is the homegrown basically. In order to not make it too smart, in order to see what neural network is doing, not the algorithm that does the mapping. And we see that with step 3, separation is much larger. So the margin, the max margin principle, like the statistical learning, is reinforced or emphasized by the neural network. And what those people found also is that the network actually learns something that it wasn't trained on. Two training data sets, this one is not published in this paper, this one is. We trained the network to recognize controls from Huntington's disease patients, and it easily recognizes them. Those are representations. Each point is a representation the way I think about it. The way the people in the paper that I'm talking about think about representation is the entire thing, the relational representation. So within the relational representation, the model arranged severity of the Huntington disease by spectrum. It did not know, we did not train it, we didn't give it information about the severity of the disease. But there is clear spectrum here from low to high. And finally, low is not detectable, low severity is not detectable in those maps, in the data, by statistical differences. Why we know that those low severity people have Huntington's disease because it's a genetic disease. We know at birth exactly that it's there. But the model learns something that we did not teach it to. So that was exciting. But the point here is, hey, we can. It was unclear in the beginning when the paper was conceived in 2013, and how do we even know that the neural network learns something useful? Or how can we know that it learns something that we didn't put in there? That's something more. And so the author of this obscure paper came up with this idea of looking at representation. But then, of course, the ideas are in the air. Word of Egg, published in 2013 as well, accepted that idea. Um, um, Talks about similar ideas, how to embed words now into space according to their uh, semantic, etc., etc. And by doing these embeddings, we can see how words evolve by taking book corpus for specific years. We can see a lot of meaning, whatever meaning is for us, we can extract that meaning from the relative location of the words. And then it was blessed by Chris Ola in his blog because he discovered how to analyze in 2015. So it's not very good to be time travelers because as I said, it's 2013 paper. People read it. So what Chris is talking about there in his Distill blog is exactly about the same. Let's look at the neural network and look at the layer. This is a NIST data set and different layers, different neural network create different representations. But again, representation is a point to me, and like that's how I hear it when I hear about it. But it's the entire kind of relation. That's what is being explored here. It's very interesting. When we do nothing, it's kind of, oh, the numbers are there. Very nice visualization. Or too sure what is there, but it looks like there will be things like that. But Loom gets interesting stuff. Okay, relation. It already has relation. Neural network enforces, preserves, or alters, or what that relation. What does it do to that relation? Notice the data relations can be discovered into D by Tisney or other algorithms that find some kind of a weak mapping. This, oh no, this is still Tisney. Take the embedding and apply Tisney. That's what we're looking for. Okay. So to summarize, take an image, throw it at a black box. Black box gives you a vector. You take this vector, take this image. Hey, this vector is a representation of that. That's one meaning. No, let's throw it out of the way. Let's talk about relationship representation. But I disagree with that because representation, just semantically for me, is like how you represent the thing as another thing. What they're saying, no, it's the map because the map contains information about relations. So is that to the paper, the Platonic hypothesis, right? And so the Platonic hypothesis, well, Plato is somewhat similar to John Conway. John Conway, if you don't know, is great topologist. He's done a lot of stuff in topology. And how do we know John Conway? Well, John Conway's Game of Life. Little thing he's done one after or something for play, and that's it. And the same as Plato. He's done very significant philosophical work. And how do we know? And I checked with my high school and other kids. It's like they only know about this single parable that he wrote somewhere in his Republic about Plato's kid that we are only seeing a shadow of the real world. And science, actually, and religion as well, are all descendant of Plato's ideas because we all think that the real world is transcendent. It's there. We don't directly observe it. Like in religion, you cannot directly see other sides, interact with God. But the same in science. We know photons are there, even though we don't see them, and atoms, things like that. Even though we don't know what those atoms are, we only have the wave functions. It's Platonic idea of the world, but Platonic idea goes even beyond that. That there is structure to the world that even our atoms are only vibration. It's if you ever done any mathematical discoveries yourself, I'm sure you applied this too, because like, yeah, I was lucky to read this sort of stuff a couple of times. It was new for me, and it was published and you don't know that. I mean, it's there. You just follow and you're like, wow. Yeah, right. So the Platonic hypothesis paper is an interesting genre paper. Basically, I would call it a review paper because it's not that this paper brings a lot of new stuff. It's kind of they're saying, hey, there's this hypothesis and this 20 paper, 20 teams working on this and showed a lot of stuff. Can we further prove or disprove this hypothesis or not? But basically, the hypothesis goes like that. Neural networks trained with different objectives on different data and modalities are converging to a shared statistical model of reality in their representation spaces. They don't show anything, not close at all. Yeah. But it's a very bold statement. It sounds good. Nothing about statistical reality you will see in a second. Will be discussed. Yeah. Well, I mean, no, they will discuss a lot of that. That's very fun. But the way they're looking at it, yeah. So it's basically what they're saying is the only thing that they're saying is if we have neural network F that maps from a data to some n-dimensional space mapping, and we have different neural networks, then we can define a kernel that takes the mappings and computes cosine distance or inner product of the representation. And then we can take two different functions, f and g, to different neural networks, and compare the kernels that they induce. So we compare the relations. We will take this produced by one neural network and a rotated version of it. And we'll find isomorphic, for example. Are they the same or are they isomorphic? So representation is our neural network mapped from input to some vector space. Single kernel is take this vector's computer in a distance. That's it. If you have a kernel, if you define the kernel, positive, symmetric, blah blah blah, so symmetric, so positions of the kernel, then you define the Hilbert space at on kernel because you define the product. But then you're saying, how do we convert to kernels? So even the kernel is the same, it's just L2, so distant, right? Or cosine distant. But F is now, you have an F and you have a G, two things. So what do, you take the data set, you map the data set. Wow, tricky. They take a mini batch. It's like the paper is filled with those tricks that throw me off, and I don't understand. Why don't you take the entire data set? Why don't you look at the mini batch on it? What is that? But yeah, those questions are unanswered. A lot of there will be more of this. I don't understand what they're doing, and they couldn't find it in the paper. But take a mini batch, map it from with one neural network and another neural network. And so now you have the embedding representation. And then in this embedding space, pick a K for K nearest neighbor, find K nearest neighbors for one, for pi, and for psi. Well, you're the specialist. Yeah, this is a person who's done deep multi-year study on Greek symbols. But the thing is that, okay, are the neighborhoods overlap? If K nearest neighbors produced by one neural network and K nearest neighbors produced by another neural network overlap, so we take a union of the neighborhoods and we see, not the union, intersection of the neighborhoods, and we see the common intersections of the ones that overlap, and how many overlap. That's our metric. Very simple. By doing that, we see that models in the vision task, so it's vision models, VITs, the vision transformers, trained with different seeds, different architectures, also CLEAV, contrastive training, classification, massive autoencoder training, all kinds of different trainings. Those that align this blue line, their kernel metric is high, the overlap is high. So the relational structure that they're learning is similar. Then they perform also higher, right? The percentage of tasks solved. To the right here, higher performance, lower performance. Higher is more aligned. Yeah, higher is more aligned. What they're doing here is black magic. I don't know. Because they're saying we use UMAP to embed models. How can you embed a model? By using weights as a vector or something? I have no idea. Nothing is claimed about weights. Although, if you talk about word-to-vec original produces embeddings which are identical to the weights of word-to-vec or matrices that it learns. But it learns representations. It's just the nature of it learns representations as activation. It's just the nature of one-hot representation of the words, selectors. In any case, okay. So the claim here on this figure is that the models that are aligned is in the relational representation sense. And mouthful, but I guess the introduction was useful, right? You understand what I mean. The models that put the neighborhoods, preserve the neighborhoods, or not preserve, that align in the way how they structure the neighborhoods. Although, here's my problem. I can structure the neighborhoods on a sphere, and I can structure the neighborhoods on a donut, and I can structure the neighborhoods on a flat space, and my local neighborhoods will be the same or similar somehow. I don't know, maybe not. But, think about it. If Disney can preserve local neighborhoods of 48 square dimensional space in two-dimensional space, why wouldn't those models be aligned in their relational sense for K and N, but have learned completely different manifolds? They could. I don't know. Okay. So again, I don't know what's on this picture, but I know what the claim is. The models that cluster together. Oh, the claim is the Anna Karenina principle, right? They brought it here. Anna Karenina, 1877 by Leo Tolstoy, and it starts with a famous quote: "All families or happy families are just happy in the same way. All non-happy families are differently. You don't have for different reasons. So they're saying, look, all the wrong models or the bad models are very different from each other. And all of the models that are high performers here from, they're very similar in their representation. And of course, the claim is, well, that's because there is this real world behind the data, and the relationship of that real world as represented by the data are useful for prediction. And if the models learn them correctly, then like the cluster. I argue nothing in this paper substantiates that claim, but okay. Then they do the following. They take language model, and they take vision model, and they take a corpus Wikipedia-based image text, where each text and each image are paired. And then they compute the kernel relational distance of the text models, Loom, etc., OpenLlama, etc., all llamas, as a line, because we have the same object, the same entity, the images tie the text. And then we see if text models, the relations within the text models, correlates with using their metric, the overlap intercept, correlate with the relations in the language models. The lines pointing upwards supposed to point out that they do correlate, but that would be that the claim is click correlates most of all. Click, as you know, is contrary language and images together. There is a huge caveat in appendix how they do. Dino V2 is a visual transformer, and they take for the vision model we use class token as a bit. For the text model, if they use the last token, nothing goes. If they average and look at blah blah blah, basically they do a lot of black magic, trying to get that correlation, trying to find the place in the model and how to average the token representations at the high level in order for correlation to happen. And okay, and they find it. They work hard on it. And then they say, what about performance? So they take models, all of the models that you saw before, plus gamma and other models that we can have, and order them by alignment to vision model and alignment again in relational sense. And they say, hey, the models that are more aligned are better performant on common sense task and on the math task as well. The relation is slightly different exponential. Well, and the claim is Platonic. There is the real world, and the models are learning to represent the real world. But I think that Wittgenstein may be right. There's nothing Platonic about it. It's just the training data. I'm a part getting Platonist. Like I would wish this to be true, but I just don't see it. So Wittgenstein said the meaning of anything is it's used in the language or in the data set. And so like I butchered his quote, but so the relations are encoded in the data set, and we saw with the faces and everything, the relations are there. And the models, the better the models capture those relations and we shift them around, the better they are. Well, the better the models linearize this. So it reached several. So I don't know who gets to win. Wittgenstein, who has only two numbers for his life, or Plato, who has shorter name, but a lot of years, but he could have lived more. The authors go further and they're trying to speculate of why what they claim is happening, which I don't solve maybe happening. One is capacity hypothesis. So on the left, you see that if we have global optimum, the smaller models will find their respective optimum, but they will not find the global optimum. But the larger models that are capable of holding the idea of the global optimum will both converge to the same because they're both able to find the global optimum. That's basically the cartoons are not. We don't. Another one is multiclass. And multiclass hypothesis is since well, there are few representations that are competent for n tasks that are for m less than. So I disagree with that on philosophical kind of like the common sense basis, but okay. They're saying that the more complex, the more tasks there are there, the more convergent are learners. The skills, the skill set should be similar for representation, similar to match to fit to all of the tasks. And I'm like, well, anyways, I think the possibilities of solving more tasks are larger than just solving one task. Like that. Yeah, of course, you how differently can you program it? Yeah, you can get very basic things like that. But we'll probably solve this with formally having model where they can pick it up with them and see, because for something like sorting, when we know everyone that's coming about the sorting, if the Platonic hypothesis is true, it should converge to the same sorting algorithm. Which one? Which one? Which one's the one that's preferred by others? Well, yeah, exactly. So lots of questions, but the figures are so basically multitask. The more the tasks the model has to solve, the more stringent it should become about how inaccurate it can be in its representations, because the same representation has to be invested. And another one, simplicity bias. We know there is simplicity bias, that there is some representation that models that's happening. And we just don't know questions. Why could be explanations of that? But because there is simplicity bias, like localism, things like that, then the number is also that's a hypothesis. Then the paper ends with 2 pages of admitting that this all actually doesn't work as well as one has to work, and one has to work. Even when, and then especially good models and something they don't align, they find their bad representations, relational representations, and other applications. Multimodal is a little bit, and they're not too, their language is completely misleading the way they write it, but they're not hiding any information. So I'm not, do they just think this way? Are they misleading themselves? And that's why their language is this very difficult to read, because I'm reading their claims and I'm like, but no. Yeah. But then they show me evidence that yes, it doesn't have to be necessarily true. Multimodal, it's a little bit of stretch. It's pretty hard to find the last one. Then I thought about Project Hail Mary, book by the guy called Marta, where the 2 legs is going. Well, they're coming engaged with dolphins, but dolphins have some vision. They're not very good, I assume. So this is like that. So the alien and a human, alien doesn't have vision; it only has sonars. But it has perfect sonars. But there is like they live in the same world, so they have the same Platonic representation. Easy to find communicate with your sensory. Easy for the novel to work. Of course. Your sensory inputs are different. So the question here is, okay, what it's like to be a bat kind of thing. If the models have different sensory modalities, different data sets, are they recovering the same structure that Wittgenstein was talking about? Because of course, our data sets are curated by humans, and they're not necessarily the Platonic world, or they may be having a glimpse at the Platonic world that's the true reality behind many many layers. They give a toy demonstration of how could in a simplified world where observation is probabilistic but still quite connected function of the true random variable, where contrasted learning can lead to same representation. Contrasted learning is metric learning, essentially. Contrasted learning learns the relative location of the subjects. So, example. Right. So, I think an interesting paper. I think if read kind of extreme, highly misleading, and but I also think they're doing a good job of stealing the thunder of all of the papers in their literature review, because those papers have substance, and this paper is more of like maybe that has a better name. That's it. And it doesn't. It's crafted name, right? It doesn't claim anything. It's like, there is a hypothesis. Well, between you that and those other people also. So yeah, I think it will be highly cited for another individuals. Well, Buddhism, socialism, the one that I started, right? The good reason is because the entity, the animal that is our society. It is smarter, but it's very slow smart. Yes, let me say. It's not particularly witty and quick. It has to really be put through brain in order to realize. No questions. I think then we are done. Right? No questions on that?
I guess my question is, what is mind check like? So there is this idea of recommendations.
Yeah, exactly.
I feel like like numerous like common knowledge that people have, but put words to it. That's
No, they do really good job in the literary. The other people are sort of tinkering
Yeah,
at the same question.
It's like kind of like Maxwell, how he took all the findings and put them together. I don't
Maxwell.
It's Maxwell before.
Maxwell is one of the geniuses. Yeah,
What's the very
today.
this one?
No, come on, no. That's a good paper.
They're claiming basically like that there's this underlying manifold of every object in reality. That's what they're saying. Basically,
I
right?
think God is real.
Well,
I mean, this, I don't know, like, it's like force around. Like, there's like a manifold, which
that's how this thought will go in history. It's very
that's the question.
I think that's the underlying hope. Believe in Platonic representation.
It's the reality. And reality is more than physical reality.
Well, it's subjective.
Well, reality is objective.
In a way,
No, your measurement is subjective, but then you're getting misled, and the reality is objective.
yeah.
It's you can have a subjective model of reality.
Yeah.
but then it's basically having a better model of reality helps to adapt to changes in environment. When environment is the same, like on an island, or like when you stuck on Earth, planet zero or the background. Well, until oil and gas run out and there's no more energy and civilization dies, then until that period, you find whatever you want. It's like that stage. Or if there's tri-solar, aliens come over to try to until reality comes in, or meteorite or something. You can believe whatever. Those who have better objective model of objective reality are more fit to adapt to change. Maybe to plan in advance stuff. I don't know. Okay. Platonic reality is a much more stronger statement than just physical reality. It's ideas. Yeah, and I for the record, I haven't subscribed. I don't know who said that. From Jim Keller. That's what I heard it from on a podcast. You think you have ideas, but it's how you.
Actually, Jordan Peterson.
It's very. He probably took it from someone. Yeah, it's a lot.
From Jim Keller. Because that's
Okay, well, it's a nice way to stop. I assume no online questions. Thanks, and we have no time.